Hello, how are you all doing today? Is my screen showing up?
Yes.
Yeah.
Awesome. Okay, cool. Um, so good morning, afternoon, evening, good night, depending upon where you are in the world. So I'm Brian, I'm from Barnard College. I'm going to present a bunch of work on responsible TinyML that I've been a part of. I'll mention some other things that the rest of the network has been a part of. I thought it would be good to just highlight a bunch of different topics sort of in this space. And I will note before I dive in that most of this is very highly collaborative work. And so I am a small part of many of these projects, and I give a lot and most of the credit on many of them to a bunch of other folks. So the motivation for me to sort of work in this space a bit is just the amount of news about lack of sort of responsible things. We've seen a lot of stories over the past couple of years around, hidden microphones and devices, TVs spying on you, all these sorts of kind of scary things from a privacy standpoint. We've also seen a number of sort of scary news articles around climate change and just the cost of doing machine learning and training these large models. And just about the lack of sort of access, something that I didn't include here, but there's plenty of screenshots of that, is a bunch of bias in models. And, we had some real problems. There was one that I remember during COVID where there was a pulse oximeter that was not accurate if you had darker skin. And so that's like really, really problematic and really a challenge. And so the motivating question for sort of all of this presentation is, how can TinyML support responsible AI? Right? Are there things we can do? Is TinyML particularly well suited to help with this problem? And so I wanted to present some work sort of in three areas. The first being accessibility of machine learning and education about machine learning and AI in general. The second category was sustainability efforts and conservation, and the last was in this sort of privacy and security space. And we've been talking about actually a lot of these this week. I think what was pretty exciting is if you go back through a bunch of the presentations, you'll see a lot of solutions to a lot of these problems coming from TinyML, and I thought I would just sort of highlight them sort of from my angle here. So let's start with accessibility and education. And so I think the first thing is, just go to the tinymledu.org website, go to our courses and materials page, and you'll see a lot of open access materials and courses that we've collected, we've made, we've shared throughout the years. And I know VJ actually mentioned this right at the beginning of this whole workshop, but there are open textbooks, there are online edX and Coursera courses, and there are materials from full university courses and a bunch of other workshops that we've run. And I think this is very important, right? Because getting the information out there and making it accessible globally is the only way that we're really going to make sure that this field is moving forward in a responsible way. If you go to the research page, you'll see a number of articles that we've published on accessibility and education. And I wanted to just highlight a recent one that was made by the whole TinyML 4D community. I just presented this at the AAAI Spring Symposium, and this should be, and I see that I made a typo when I put it onto the website. It's Spriggan. I will fix that later. And this should be coming out fully in its like PDF out into the world in the next month or two. So what was sort of this paper about? Well, this paper was sort of about summarizing a lot of the efforts that we've done over the past couple of years and why TinyML, we think, is a really exciting, and it just embedded machine learning in general is a really exciting opportunity for education, but also why there are some challenges, right? And so as you've sort of seen this week, as we've discussed, it's low power, it's low cost, it's low connectivity. This means it's low resource requirements, which means a lot of people can easily use it. It's interdisciplinary, right? There's machine learning, there's embedded systems, there's IoT, there's all sorts of different things, which is really exciting because you can come at it and learn about it from different angles, and you can teach it in different contexts. And there's a lot of applied learning, right? There's a lot of applications. You've seen a lot of applications this week. We've mentioned a bunch of applications in passing, and there's a lot of really exciting and good applications which you can use this for in your world around you, which is exciting for students. On the flip side, because there's so many microcontrollers, because it's so cheap, because there's such a proliferation, there is a lot of fragmentation in hardware and software tool chains. So you might be able to get your hands on a microcontroller that could run TinyML, but it may not work with the particular example that, say, we made for the Arduino. Also, while these sort of devices are, quote, low cost, that's not actually low cost in many countries, and also there's some huge tariffs and shipping costs that we've heard about recently trying to get these devices into certain places. And finally, we've put out a lot of open source materials. They're mostly in English. That is not necessarily sufficient for many places. I'll give Marcelo a lot of credit, and Diego and all the other folks for actually, there's now a lot of materials in Portuguese and in Spanish, which is wonderful, and a lot of more locally relevant examples, and we need to keep building that there. And the sort of interdisciplinary nature of it makes it really exciting, and you can teach it from different contexts, but it also makes it hard because you kind of need to know a little bit about a bunch of different things to teach that. And there aren't so many research venues yet, but that is sort of growing. And so I'm sort of hopeful that we will, and we have been, overcoming a lot of these challenges. So sort of with that little bit of context, last summer, we convened a group of folks for a different, ICTP workshop. We actually went to ICTP. It's the picture on the right left. I don't know how your screen is mirrored. It's beautiful. You should try to get there at some point if you can. It was a lot of fun. We were like in a building like right behind the trees over maybe here-ish. And we sort of sat down with a bunch of the folks in this network to try to think about how can we improve the sort of offering and accessibility of TinyML education. And essentially what we came up with was that we need to continue to formalize a more modular curriculum. We have a lot of materials up there, and all of the materials sort of touch on some core concepts, but then build on it in different ways. And so our sort of suggestion for you and for ourselves as we continue to build out this educational content is that there's a core of machine learning and deep learning. There's a core of data-centric AI, right? You've heard a lot about how do we get data sets, how do we collect data sets, or at least I've heard that appear a couple of times. There's a core of embedded systems. We're doing this on microcontrollers. And there's some responsible AI components that I think are really important that should be included all the time. And as we did some hands-on examples this week, I think the exciting thing about TinyML and embedded machine learning in general is that you can teach it through examples, which I think is really important because it gets people excited, it connects theory to practice, and it makes things really powerful and real to students. But there's a bajillion optional modules. You could come with a hardware focus, you could come with a software focus, you could embed this inside of a domain-specific course, and these courses could be of different lengths, right? We're doing a 1-week workshop. There's the edX-style micro-credential courses, there's full semester-long courses, and I think these sort of concepts can be taught in different ways. And so as we go forward, basically my comment is, please go to our website, remix our course materials, and please consider sharing it back, because we'd love to build that full modular curriculum, but we're only going to be able to build that together. We're only going to be able to build that through everybody taking things, sharing things, doing things in different ways, and then sharing it back. And then eventually we can actually have this sort of repository library organized in such a way that it becomes easier and easier for folks to teach their own courses. So yeah, calls to action was exactly that. Not only remix it, there's a bunch of other things we need to work on. And if you're interested in any of these things, or these things are exciting to you, please reach out, please collaborate with us. We're only a couple of folks, but we're trying to do a lot of good here as much as we can. So there's a bunch of different things here. We should do formal assessment of our educational programs. That would be an exciting project to do. We need to maintain all this open source software and courseware. That's challenging. We should be collecting more models and data to make things easier for people to do examples. We can continue to make hardware more accessible. We can continue to grow the research community, right? As was being discussed this morning, there's very nascent research on-device training. That would be exciting to grow. That would be exciting to build a community around. And one I just wanted to mention is that, we need to improve on our outreach and diversity efforts. And I'll show you some sort of sobering data that we recently collected. I was doing this in the context of robotics, but on the table is also AI and systems, which is, tiny machine learning. And if you look from a gender ratio perspective, it's not very good. This sort of area of AI, ML, robotics systems is sort of 10 to 12% female. And of course, lots of caveats around bias and misperception and non-binary identities here, but I point this out not to say that this is definitive, but just to say that we need to keep this in mind, and we need to work together to bring together and improve our diversity of our community. So that's a rapid fire sort of set of topics around accessibility and education. Happy to answer, tons of questions about that. Now at the end, I don't know, Marcel and Marco, feel free to jump in if you want. I can also just plow ahead and keep introducing sort of all these 3 core topics at a high level, and then we can have a discussion at the end, whatever you all think is best. I'll pause if you want to interrupt me. But if you don't, I can keep going.
Let's see if there's any questions in the chat. There's congratulations for your presentation and for the workshop at Triple AI. And no questions up to now.
Okay, cool, great. I'll just keep going then, and feel free to interrupt me if you want. So if we're going to talk about a little bit about sustainability and conservation, I'll point out that there were a bunch of talks this week. There's a bunch of papers up on our website about this. And the one I wanted to mention a little bit in detail is one that I worked on with VJ and some other folks at Harvard and Stanford, trying to come up with not a application for sustainability or conservation, but trying to understand the overall sustainability aspects of TinyML. That is sort of, we know through these examples that TinyML and embedded machine learning can support UN SDGs, but it comes at a cost. And so the answer is sort of, what is the net impact? And we wanted to sort of build up this model here where we can deploy it, we can work on all these SDGs, we can do great things. We know that using the device consumes energy though, right? And that energy has to be provided from somewhere. And so there is like a cost there, but there's also a lot more costs. If you want to get the device, it needs to be manufactured. It needs to be shipped. At the end of the day, it ends up getting thrown out. And sometimes there's recycling and sometimes there's upcycling, but there's also a lot of these all embodied costs and not just the operational costs of using these sort of products. And so we wanted to try to do a high level analysis to sort of start to look at this and try to understand from a system perspective, do we think TinyML will be net positive as it stands or net negative for the environment? Just to keep this in mind and to try to refocus our efforts in the correct directions. So to do that, we sort of built some representative systems. So we thought about like a high cost, a medium cost, and a low cost TinyML system. The high cost and medium cost were image classification systems because cameras are kind of bigger and bulkier and actually will require just a physically larger device. And the low cost one was a keyword spotting example because the MEMS microphone is pretty small. And so we sort of took these canonical devices and we tried to understand sort of what is their total environmental impact. To do that, we actually built this fun little footprint calculator. You can actually go to this website and you can we have our sort of 3 predefined examples, but you can kind of go in and customize all the values and say, hey, I actually have this thing or that thing. And it will start to spit out a carbon footprint for your devices, which is, I think, pretty fun and exciting. Credit to Shotank and the rest of the team for sort of building this. And so if we take this and we sort of try to put this in context, right, what is a little device? So Apple actually has done a really good job recently reporting the footprint of their devices. And so this is from a couple of years ago, I think, the raw data at this point. But if you look at a MacBook Pro versus an Apple Watch, right, as the devices get smaller, their carbon footprint shrinks by about a factor of 10. And so we go from, 349 to 34. But then when we do our representative TinyML systems, we'll get another savings of 5 to almost 40 times, depending on if you're a high-cost TinyML system or a low-cost TinyML system. And interestingly, unlike some other presentations I've seen recently, the cost of compute is actually very low here. What sort of dominates the cost of these TinyML systems from an environmental embodied carbon footprint angle is actually just the physical size and all this stuff. It's like the casings and the cameras and all those things are so much bigger than the actual tiny little microcontroller. And microcontrollers can be made on lower costs, older technology process nodes. And so they're just fundamentally not the overwhelming cost here, which is sort of interesting. But we wanted to go farther than this. It was nice to build sort of these representative systems. And if you go look at the paper, there's a lot more detail about sort of how this gets built up and what the proportions are. But beyond just the cost of one, the question is what happens, if you scale it to the world, right? And so right now there's sort of an estimate of around 15 billion IoT devices. They're not all TinyML devices. Let's just assume they are. If we do some sort of growth over the next couple of years, you can, or next 100 years, you can pretty quickly get to 250 billion or a trillion sort of microcontrollers deployed globally. Now, probably the growth won't be totally there, but there is an estimate that there's 250 billion microcontrollers today sort of out there. So like, let's make a worst case assumption. Let's take that high cost TinyML system. Let's take 250 billion TinyML systems deployed globally. Sort of what's our net impact here? And it's a very non-trivial, 1,700 metric tons of CO2. That's like a very, very, very big number. However, if we start to look at some of the savings you can do, there's some interesting papers that show that for a building, if you have a smart HVAC system, you can save about 20% of your energy cost. And so if we take residential homes globally, which is about, I think it was like 8% of total carbon emissions, and let's say we make them all smart because we put little tiny ML sensors all over the house that allow you to, see if somebody's in a room and turn off the lights and turn off the AC and set the different zones correctly. If we just assume you can hit that sort of 20% number on that 8% of carbon emissions, like just in residential homes, I'm not including commercial buildings, we can actually save most of that cost, which is pretty exciting. And this only assumes sort of a 3-year lifespan for these devices. And then if we take like the rest of the world and all the other, emissions, and we have a 0.6% savings in those other sectors, then we're break even. And if we assume we can get, 20% in all those other sectors, then we're super, super, super positive for the world. And if we have devices that live more than 3 years, they live 5 years, they live 10 years, this all gets better. And so while this is sort of hand-wavy, directionally correct kind of numbers, and I wouldn't take any individual number as sort of the gospel, I think directionally what this is sort of saying is that if we take some subset of our TinyML devices and we deploy them towards sustainable aims and conservation aims, it is very likely that all of TinyML will be sort of a break-even or positive endeavor for the environment, which we found very exciting and sort of uplifting. Now, of course, huge limitation being here, you actually have to deploy them for good. But I think there's a lot of people on this call that want to do that. And I think, if as a community we are careful and try to build some systems that can do this sort of thing, we can actually have a net positive impact on the environment while making technological things that usually often people think of as being sort of net negative. So that was actually some super uplifting and exciting sort of notes from us. And there's a lot more data in the actual paper, and there's a lot of really cool examples in some of those other papers and a lot of what people talked about this week. And so I hope that you dive into that stuff if you find it super exciting. I'm not seeing more questions right now, so maybe I'll just keep going and then we can circle back around at the end. So education, accessibility, really exciting opportunities for TinyML, some challenges. We need to work together as a community. Environmental sustainability and conservation, some really exciting opportunities for TinyML, but we need to actually do it and work together as a community. And you'll find with privacy and security, same thing. Lots of exciting opportunities for TinyML to help towards a responsible future, but also some real challenges. So where am I coming from privacy and security? I'm thinking a lot about just private information, cameras everywhere, microphones everywhere. This is potentially a challenge. We're moving into a world of lots of surveillance and lots of opportunities for that data to then get hacked, stolen, leaked, which is not good from a privacy and security perspective. And I think we're going to find that TinyML is like soon everywhere, right? Like we've had all these IoT devices and they're getting smarter and people are putting, chips in them. There's now even like a smart toothbrush that you can like talk to. And so I think we're going to see these things everywhere. We need to be careful to design systems that uphold the best values, best ethical values. So recently, some work that I was on, again, with VJ and Pete and Matt and some other folks, was thinking about what are sort of the impacts of this on a global scale, and how can we think about design paradigms to help promote privacy and security. And the idea here is that normally you have these sensors, and then the data is like collected in a processor, sent to the cloud, something like that. And generally, the way I would think about this is, you have a camera, it's recording video, it's sending it to the cloud for analytics, right? And what does that mean? Well, that means the raw video is over the internet. And yes, it's probably encrypted, and yes, they're probably doing their best to keep it private, but there's still just tons and tons of frames of images just sort of like going to the cloud. if we take a TinyML viewpoint, we can actually embed a machine learning model like right at the sensor. And then even if you have like a coprocessor on board that's doing something or whatever, right? You can embed into the sensor, say this is an example of Pete's, person sensor 1.0. You can embed a person detection device model right in the sensor, right at the camera, and then this little unit has only a couple pins coming out that basically say yes I saw somebody or no I didn't see somebody, right? And if you do that, now suddenly yes, there's information that can be leaked. Yes, if somebody's in, you could potentially hack and figure out if somebody's in the room, but you'd never get the raw image because the raw image is never transmitted anywhere. It's processed right on the device and it's thrown out, right? And we're just getting this 1-0, yes, somebody was there, somebody wasn't. And you can imagine a lot of different things where really what I care about is the binary result or the trinary result or the low dimensional results that comes out of processing some raw data. And I don't really want the raw data. And this is also good from a bandwidth, energy consumption, latency perspective, but from a privacy perspective, it also, by design, ensures that raw data isn't going places. You could also think of this as your Alexa, Google Home, Siri devices. I won't say the correct buzzwords, or maybe I did, and I apologize if I just turned on all of your devices. But if you say, whatever that word is that turns them on, right? There's an always on thing listening there, and it's spinning and it's saying, hey, did I hear it? Did I hear it? Did I hear it? Did I hear it? But it's not sending the information to the cloud. It's not distributing it. It's just sitting there in a low power state. And then when it hears it, it says, hey, let me turn this on. Let me actually record. Let me send that, and then it's not spying on you. It's not leaking your private information. At least that's what they tell us. No, I'm pretty confident they're doing that. It was actually kind of funny. There was recently a guy on social media who's constantly like pointing out security things, and he was like, nope, ran Wireshark on my new Alexa and like doesn't send anything until I like tell it to, and that's because it's processing locally. So this is good privacy by design. And we were calling this sort of the machine learning sensor, right? And then we were thinking a little bit more about this and we're saying, okay, this is great, right? We're going to do this. The problem is now we're going to sell you a device, a very small device. So instead of you buying a camera, you're buying a person sensor camera. But now it's got some embedded model on it. So now there's like this whole machine learning component to this product that you're buying. Oh, and by the way, you can go to mlsensors.org to see a little bit more about this whole project. But we were then realizing, shoot, like normally when you buy a camera, you get a data sheet that tells you sort of plug this in at this power, it works this well in these ranges, the accuracy is this good or not, all these sorts of things. And this is, this is great. You can use this if you're a engineer. You can look at a data sheet. You can know how to integrate it into your system. You know the pros and cons. You know where it will fail and where it will succeed. Unfortunately, now I've sort of embedded this machine learning model into your sensor. I'm selling you a sensor plus machine learning package. Now you don't actually really know when it fails, when it succeeds, what the bias is, all these other sorts of things. And so we were proposing, okay, so if we're going to have these machine learning sensors, now we kind of need a data sheet specifically for these kinds of devices so that all that information is transparent and available, right? And so we were saying you take sort of those standard data sheet components, which are the blue ones sort of at the top here, and then you have to build on and add new devices, new sections to your data sheet. So you need something about IoT protocols and encryption and how it's sending the information back and forth. You need something about the actual like model, right? How is the model trained? What data set was the model trained on? Can you tell me something about the bias in the model? Can you tell me something about the bias in the data? And there's actually really good tools and suggestions out there like model cards or data sheets for data sets or other sorts of things that you can use in sort of this meta data sheet. But we need to be careful to ensure that those things appear, right? In order to start to be able to understand and evaluate the device that you're buying. And the last one is that you need some other things that people haven't really done before, right? You need some environmental impact statement. And we were sort of saying, hey, you could use the environmental stuff the calculator that I just presented, or you could use, another one. And importantly, you need end-to-end performance analysis, right? Because your model may have been trained using one camera, you're now deploying it with another. That's going to introduce bias and errors and issues. And so somebody needs to actually take this device, and we ran a pilot study at Harvard. It was kind of fun. We did the whole person sensor thing. We took Pete's production device or an earlier version of the device. We made an open source one, and you can see our open source plans online. It was based around the, I think it was RP2040. I actually blanking on exactly what chip we used, but we built an open source one. And so we put them on a wall, and we had like a ton of students walk by into the room, different clothes, different heights, different genders, different ethnicities, all these sorts of things, like come into the room, and we tried to sort of do a little low light conditions, high light conditions, and we tried to provide some sort of like end-to-end metrics on it. And unsurprisingly, like we found some bias. The data set we had trained on was sort of standard, I think it was MS COCO, basic data set. It's got bias in it. That bias sort of plays along to our sensors. We found sort of different drop-offs on accuracy. If you were close, really close, that was okay. If you're really far, it wasn't. Not super surprising, but I think these sorts of analyses are important to include in these data sheets, because then you as everyone on this call is now a little bit more aware of machine learning and embedded devices and all these sorts of trade-offs. But if you're just an engineer out there, or you're just you're building some, you're an HVAC engineer and you're building a system to turn on and off the HVAC, like you just want to know, does this device work? How well does it work? Oh, its range is only, actually accurate to 10 feet. I should put, one on both corners of the room instead of just in one corner to actually get the impacts that I want, right? And so, our purpose with a lot of this ML sensor work is more to say, not that this isn't already happening and people don't know that they need to know this, but like we should be very explicit about the fact that these are important things. They must be included. We need to start adding them here so that we can ensure that there is transparency. We know what's going on, and we can start to build systems that actually are good and fair and not biased and protect privacy and all these sorts of things. And recently we extended this work, one step further, which is that we worked with a bunch of social scientists and ethicists and philosophers to try to think about, from an ethics standpoint and a philosophy domain, what does this mean, right? If we're moving to an age of perversive AI sensors, what are the risks and what is the materiality of this, and how does this sort of impact each other? And so what we did is we did a little bit of a, and you can go to this link and you can find it, and I'll post all the slides with all the links and all the names on the website. But we sort of did like an evolution, right? Where like sensors started, or a lot of these sort of the sensors as we know them today started in, the 70s, 80s, 90s, and we had microphones and IMUs and thermometers and CCDs for images, right? And they were these sort of static things that existed and sort of gave you the raw analog output, or maybe slightly digital output of some of these sorts of things, Then in the 90s, we moved to connecting it to the internet. We built IoT sensors. We had, wireless CCTV cameras, or even wired, that would send information to the internet. And we would just look at the footage. And this was very exciting. Suddenly we could, you could monitor your building from far away, Then we started adding AI into these IoT sensors. So you had sort of like the Ring doorbells and the Nest thermostats. And originally these things sort of did a lot of computing in the cloud. They would take the image, they would send it up, they would compute in the cloud. Recently, we've been having these edge AI sensors, right, where there's some local processing, right? There's not only local processing, but there's a decent amount of local processing, because otherwise they'd run out of battery, right? Like if your Apple Watch was actually sending the audio to the cloud to listen for Hey S all the time, it would die in like, I don't know, 20 minutes, an hour. Like it would just, the battery life would be horrendous. And now finally we're getting to these true, TinyML ML sensor type things. And so we're now actually really embedding all of the processing right at the edge in some cases. And so as you think about sort of this evolution of sensors, and it's driven by, economic and material gains and desires and needs. And I think sort of what we lay out in the paper is that probably we're only going to get more and more of these things. It only makes sense. They're positive economically for many companies. They provide you with more gains. We will see more of these. What are sort of the risks, right? And we were sort of looking at the impact on responsible AI at a large scale, using some sort of more social sciencey theoretical like terms, thinking about validity and reliability, safety, security and resilience, accountability and transparency, explainability and interpretability, whether they actually support privacy, and do they manage bias, and are they trying to promote fairness, right? And we sort of colored the risks to try to think about and discuss this conversation. And essentially what we're seeing is, traditional sensors kind of just like gave some data. And so they're pretty low risk in general because they kind of just like, here, data. And right, as you add intelligence, sort of the risks kind of increase, right? Things get less explainable because there's a machine learning model in the middle. We don't really know how to explain that. Things get less transparent because there's all these different sort of systems going on to get it. It's less secure, it's less private. The information is flowing, through the world. It may be less valid. We're not really sure. Is it reliable? If we lose the internet connection, does the device fail? And we're sort of a little bit hopeful and a little bit worried from the TinyML ML sensor standpoint that by embedding the machine learning model at the edge, this overcomes some of these challenges, but it also introduces new ones. The explainability and interpretability is still pretty bad. Can we manage biases? It's unclear. Can we even update the model if we know there are biases? Maybe not if it's burned into this device, deployed remotely somewhere across the world. The reliability testing is very hard, right? Because now we're running small models that have lots of approximations and quantization at the edge on different kinds of cameras and different kinds of systems. It's very hard to tell. So we sort of, in this paper, no real solutions yet, but a first step at trying to lay out the problem and say to the community, hey, here's a lot of things we should think about. Here's sort of the physical nature of where computing is going. And the fact that you have to take into account the actual hardware, the actual deployed scenarios when you think about risks in order to make sure that we build systems that are actually responsible in the future. So that was actually me talking way faster than I intended, but I tend to do that often. And the idea here was just to sort of lay out a little bit of the journey and the possibility of responsible AI in the context of TinyML. And my overall story here, right, is I'm pretty bullish that embedded learning can actually be quite good, right? And we can provide more privacy over some certain systems. We can channel it towards responsible, sustainable aims, and we can not use so much power when we train and deploy these systems that they actually are pretty efficient. And I'm bullish that using these sorts of things increases accessibility and educational opportunities. You're all here learning about it today. You can relatively cheaply get some hardware and try to use it and bring it into your classroom, and it will increase sort of AI literacy globally. That's my hope. But I think there's also a lot of challenges and a lot of things we have to be careful of to make sure that we keep pushing towards improving across these domains and not falling into traps where we can, not use it. We can just say, oh, it's probably good, but nobody needs to build that good system. And so then it never gets built. And so I think we need to keep this sort of top of mind moving forward. So that was sort of all the slides I had. Happy to open up to questions. Happy to chat more. Let me pull up the chat too and see what's going on.
Thank you. Great presentation, Brian. Well, it's overwhelming. It's a lot of things. Brian, it's interesting. We start the week with the history of artificial intelligence. We passed for several presentations talking about what happened with the TinyML. You show here about with the focus in sensors that how we came from the 70s to this decade in this century. In parallel, we saw a lot of presentations also talking about the let's say the buzzword of the moment. It's generative AI. We saw that people we are starting to see the generative AI going to the edge. Mainly the same thing, the same stuff that you talk here. It's problems with energy, problems with problem related with the security, privacy, and so on. So we can see that like a generative AI is going for the same path that we saw with the TinyML and the data that was collected from sensors. How do you see the future of generative AI? Is the same as TinyML? There is some kind of a marriage for those words. What do you think about that?
Yeah, I mean, I think that's a big question that I don't know the full answer to. But let me take a stab at some of that. So I mean, on the one hand, generative AI is just another machine learning architecture, and there's no reason that it can't sort of follow the same process, and we can't start, coming up with really good for the world use cases, and we can't start finding efficient ways to, train and fine tune models that don't require a gajillion parameters and, the energy usage of countries to train, right? Um, at the same time, I think right now we're finding that scale is really important with generative AI. And it seems that we haven't hit the point yet where more scale isn't just a good thing. And so there's a little bit of an arms race to make models bigger and bigger and bigger and bigger to get better performance out of them. And so you're seeing data center costs being exorbitant, and thousands of GPUs running for hundreds of hours to get individual models. So I think we're still sort of early days on this. I'm a little worried about the just huge growth in size, because the power of these models is seductive and really awesome. I mean, it's amazing, right? Like, you can do amazing things with these models. Um, the fact that you can come up with like a high level prompt and it can generate a conceptual image for a paper for you is crazy. But at the same time, how much energy did you use? There's a lot of hallucination and bias here. We're very undertrained, so I think we're particularly suspect to some of that stuff. So I think we have to just sort of keep these things in mind, right? Like, how do we keep generative AI education accessible? Like, we're not going to be able to train a billion parameter model in class. Is there a 1,000 parameter, tiny version that's maybe like not very good, but can learn a couple of things that we could sort of train? I see this as sort of, Apple's keyword spotting model is amazing, right? It's very good. So is Amazon, so is, Google's. I can train one that's pretty bad with 60 or 90 examples, but it's really cool, right? Because I did it and I picked my keywords, and I did it in an hour. And I'm hoping that we can get sort of similarly there with some of this generative AI stuff. But I think time will sort of tell. How do we use this? How do we deploy it on premise? How do we find ways to compress it? There's been a lot of recent work on 1-bit LLMs and some other really crazy things. So I think we'll get there. I think a combination of the computer architects and the algorithm folks trying to work on it will get us there. And I'm hopeful that everyone who's working on explainable AI from the model perspective, we can take that learning and still apply it to these transformers or GANs or whatever model architecture comes next. And I hope we can see machine learning as sort of a not generative AI as anything different, but just a new and exciting way of using machine learning. And then we can apply all these sort of similar processes that we've been working on to there. That's my hope.
Fantastic. Thanks a lot.
Yeah.
Folks, some questions. You can open your camera, your microphone, and use the opportunity to ask Brian about his research or what have been done.
I know I covered like 4,000 things in 20 minutes. So you can also feel free, to ping me on Discord or email or whatever later, and I think I guess I'll say I'm also excited to see what you all come up with, because I think there's sort of infinite applications of this technology, and the real key here is that as it's a little bit more accessible, I think we can sort of customize things for your local needs. You can take the system and you can go ahead and solve a problem that matters to you. And I think that's where we'll see the real biggest impact here, right? Like, do you need to figure out how to get rid of mosquitoes in your local pond? There was that really awesome project where the person built a little solar powered thing. Actually, Marcelo worked on some of the mosquito wing beat measuring, but there was an earlier prototype, I think, that didn't have a sophisticated machine learning model, but just basically like spun a little agitator, had the water move. It was on Hackster, and then it like could, drown some of the mosquito eggs. Like, that's amazing, right? Like, that was a huge problem for them locally. Boom, built it, solved it, right? And so I think playing around with these embedded systems, being able to imbue some intelligence, I think this will lead to really awesome stuff beyond my wildest imagination. So go do cool things and let us know how we can help.
Super. Thanks a lot, Brian. Thanks a lot for all your fantastic work that you have been doing with education. It's fantastic. Thank you very much.